All right, welcome back, everyone. Let's take a look at another concept of an internal stress, and we're going to look at this, and we're going to call this transverse shear. We've talked about shear before with something called direct shear. Direct shear was like if I had an object and I had two forces and they were separated by almost no distance, and it would just cut the thing in half, like a bolt holding in a connection, a bolted connection or something. So, this is slightly different because what we're saying now is we don't have a direct force. Instead, what we're doing in this case is what if we took this beam and we put a moment on it, we bent it, right? So it's making some sort of smiley face type thing with that positive moment. And we want to know, does that also create some sort of shearing force? If we were to do this, I think the best demonstration is if we were to take a beam that was made up of multiple smaller pieces. In this case, what, one, two, three, four pieces, and they were unbonded, meaning there's no bond in between each layer, and we were to bend it like that, you can imagine what's going to happen to the end. The end is going to almost like stagger step, right? Because the reason that's happening is because the top is trying to get smaller, the bottom is trying to get longer, and in between whatever step we look at, there has to be some sort of horizontal or I guess I call it longitudinal force that's causing that to happen. So if we were to bond it, if we were to glue these pieces together, then we get something that looks like this little blow up on the right, where now we have a straight edge. But in order to have that happen, we have these internal forces along the length of the beam. And those internal forces are really what we're calling a shear stress. Now, if I were to take a little element and zoom in on it and blow it up down here, this is sort of what's going on is everything is in equilibrium in this class, like or in mechanics of materials, we assume everything's in equilibrium. That means that our net force, or some of the forces in the X, some of the forces Y have to be equal to zero. Well, we just said there's some sort of force that's pulling it horizontally. Well, that means there has to be an opposite force on the other side of the element that's going horizontally to the right. And then same idea with up and down. So as we move from left to right, we say that we have a shearing force going up, and we have a counteracting shearing force going down. That's really what we're looking at when we talk about transverse shear stress. So how do we find it? What is going on? What mathematically, how do we find this internal bit? Well, as a review, we talked about internal forces. If I were to cut a beam anywhere and say what's going on internally inside of a beam, we said there were three types of forces. There's an axial force. That's the first thing we talked about, either tension or compression. There is a shearing force, which is perpendicular, or sorry, parallel to the surface. And then we have a bending force or a moment, right? Well, we've already talked about two of these internal forces and what stress they get. For the axial force P, we said that our stress is P over A. It's the same throughout the depth of the beam. Meaning if I'm at a point here, 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 it's always the same for our axial force, our force P. And then from our bending moment, though, it's not quite as simple. We saw this before where we said, well, the top, this is assuming we have some sort of positive moment, making a smiley face. The top is trying to get shorter, so it's in compression. The bottom is trying to get longer, so it's in tension, and in between, it linearly changes. We talked about this part in the center being the neutral axis where there's zero stress, and we had an equation of mc over I. Where c was this distance up to here, right? And we had negative c going down, all that good business, and negative is compression, positive tension. Well, so that's two of the three. The last one we need to look at then is what about this shearing force? What does that give us for stress? This is what it looks like. We end up with this parabolic shape, right? So we had straight up linear, we had linear at an angle. Now we have this parabolic shape where it's maximum at the center and it becomes lower and lower, lower as I get to the top and the bottom. And we'll see why mathematically why that is in just a second. I'm not going to actually derive it just because I'm trying to keep these videos shorter. But for an equation for how we'd find the shearing stress we have something like this here. The shear stress, and it's the same variable we used for shear before with tau. We've seen that for torsion and torque. We saw it with direct shear. Same tau is equal to VQ over IT. So what are these variables? V is the shearing force. Now, in direct shear, we had a force that just looked like that, and it was V. This is different because it's not right there. Like if we just said, if we had something like this, we would still have a shearing force. So instead, where do we get it? We get it from a shear diagram. We've done moment and shear diagrams before, at least you should have in statics, and yeah, also in this class, right, when we did our bending stresses. So from the shear diagram, that's where we're getting this V variable. You can find your maximum shear or where it's zero or whatever else. I, moment of inertia, we've seen that before. 1/12 BH cubed is the most common for some sort of rectangle. T is the thickness of our cross section. So if you have a rectangular cross section, it's just that thickness T, that width right there. If I had like a T shape, I would have two thicknesses, one here and one there. So I'd have two different shear stresses as I move up and down that cross section. We'll see an example of that in a little bit. And then the last variable, Q, I saved it for last, the worst for last, because Q is definitely the hardest to find. It's what students struggle with the most. It's called the first moment of area about the neutral axis. So let's talk about Q, because Q, like I said, is the hardest. There's the equation for Q. Q is equal to A prime Y bar prime. So you might recognize some of this stuff. Y bar is like a centroid. So yeah, it's the centroid of this little shape. A is just area. So let's see how that works. So let's say I had a 3 by 12 cross section, meaning this is 3 inches wide by 12 inches tall. And I want to find Q at various heights. Let's start with Q at the neutral axis. This is the maximum Q that I can have. And because it's the greatest Q, it's the largest Q, it'll be also probably the largest shear stress. In fact, it will be for a rectangle. So regardless, so how do I find it? Well, we have our equation, A prime Y bar prime. What is A prime? A prime is the area above the neutral axis. So that's 3 inches times 6 inches, right? That's the A prime. What about this Y bar prime? Like I said, it's a centroid. So what's half of 6? 3, that's its centroid, its distance away. Multiply all that together, and I get 54 inches cubed. Now, one way I like to describe what's going on here, what the first moment of area, we know the word moment, right? Moment is like a force times a distance. And we have seen this for like say we had a beam and I had some sort of distributed load, and the moment of that distributed load is its area times its centroid away. Well, this is the same thing. In fact, I tried to do it kind of like a 3D thing of exactly what we're looking at. Let's say you're hovering above here like a bird and you're looking down like this is a plan view, and you want to say, what is the moment from this shaded area about the neutral axis? So you could pretend it's like almost like has a density to it and it's trying to rotate around that neutral axis, meaning into the page. Well, if I tried to draw it 3D, I can see my 3 inches by 6 inches. And then you can imagine all these forces down along this rectangular shape, and its centroid is in the middle. Well, how would I find the moment? Well, the area, 3 times 6, times this distance away from the neutral axis. So that's I don't know, that visual may not help. I made that up, so copyright Todd Fonts. I don't think anyone ever used something like that. But what happens is with this Q is it varies based on where we are looking on the cross section. So let's say we want to know the Q 4 inches down from the top. Because it's 6 inches, that means 2 inches up from the neutral axis. Okay, well, the area is pretty easy because this width is still 3, this height is still 4, so I have 3 times 4. What am I doing for the centroid distance away from the neutral axis? Well, the centroid, because it's 4, half of 4 is 2, but I have to get all the way down to that neutral axis, so I add that other 2. 2 plus 2 is 4, giving me 48 inches cubed. Well, let's do one more example. What about 1 inch from the top or 5 inches from the neutral axis? Well, the area, once again, is easy. It's just 3 times 1 for a total of 3. What am I doing for its centroid distance away from the neutral axis? Well, this little distance in here, because it's 1 inch, that would be a half an inch, right? but then I have to get the rest of the way down, which is at 5 inches, multiply that together to give me 16.5. And what I see is it's not only decreasing, but it decreases exponentially. So as I move to the top, what's happening is there's two factors in here. The area is getting smaller, but also this y bar prime is getting smaller. So together we're getting this parabolic shape or parabolic difference, I guess, right? And I didn't mention this in here, but it is the exact same if I were to do it from the bottom. So if I were to do 1 inch from the bottom instead of 1 inch from the top, I get the exact same value, right? If I did 2 inches away going down instead of up, I would get the exact same value. So I get this symmetry to it too. So going back to our equation, tau is equal to VQ over IT. Well, the shear typically isn't going to change. We're at one place on that beam from our shear diagram. We have that shear. The moment of inertia typically isn't going to change. You know, if it's a rectangle, it's a rectangle. The thickness, it typically isn't going to change unless you have an abrupt change, like I said earlier. But otherwise, if you just had like a rectangle, it's the same T throughout. So the only thing that changes is Q. So because Q is changing, because it creates a parabolic shape, this is our Q profile. I mentioned this earlier, we have a maximum Q. The most Q we can have is right at the neutral axis, right? Maximum Q possible. That means we have our maximum shear stress right here at the center. This is the opposite of when we had a bending stress, which look like this, right? With the bending stress, with tension and compression, we had our maximum at top and bottom. For our shear stress, we have our maximum right at that midpoint, and it's zero at the top and bottom because Q is zero at the top and bottom. So, what else can I tell you? I guess that's it. Let's go ahead and take a look at an example before this video gets too long and out of control. It's probably already too long. And let me move my toolbar up here. Let's see why. There we go. Let's get black. All right. So let's say we have this example. We have a beam with a 200 pound per foot distributed load, 8 foot span, and we want to find the maximum shear stress. It is an I-beam. Decided to pick kind of, but it is a symmetric I-beam, which makes it a little bit easier. So how would I solve this problem? Let's solve for the variables outside of the problem, meaning let's start by finding my maximum shear stress, and I'm going to do that using statics and a shear diagram, because that's where we're going to get it from, right? Diagram. And so from that, as a review, well, this whole beam is symmetric. So AY and BY are the same, right? It's just 200 times 8, which is 1600 divided by 2. So this would be 800 pounds, and this side's 800 pounds. I'm not going to spend time doing that just because it should be super basic by now on how you do that basic statics. Drawing the shear diagram then, what do I have? So let's draw a little baseline here. And I'm not going to draw the moment diagram since we're not dealing with that right now, but this is shear. Our unit is pounds. We start off with 800 on one side. Let's use green. Maybe green will show up a little better. So we start off with a positive 800. We decrease by this area, which is negative 1600, bringing me down to negative 800 over here, minus 800. So that's kind of what my shear diagram looks like. What is my maximum shear? Sign doesn't really matter as much, but in this case, I'd have a maximum shear. I don't know where I'm going to put this. I guess I could put it right here. So V max then is equal to 800 pounds. And if I asked you what is the shear stress right here at the midpoint of the beam, you could go down and, well, shear is equal to 0. So my shear stress is equal to 0. Cool. So it's right at the supports. And this is actually really common. In fact, in structural engineering, we design for a maximum shear stress at the supports by adding extra little plates or gussets and things like that, right? All right, so that was step one. Step two, let's find our moment of inertia. And this is an I-beam. For a common shape, you could look it up in a table. I have a little I-beam right here. This is the same I-beam, just copied down so I can draw on it easier. But I could use the same one, or I could look it up on a table. I could also break it into 3 different shapes and use parallel axis theorem. I'm actually going to use a totally different method altogether and say, well, I'm just going to take the moment of inertia of the outside, meaning if I treat it like a rectangle, and I'm going to subtract out these 2 inside rectangles. So if I did that, I would say that the moment of inertia about the neutral axis, that midpoint, is equal to 1/12 BH cubed. Well, this is for that outside rectangle. So 8 times 8, 9, 12 cubed. And then I'm going to subtract out those 2 inside rectangles. So they're 1/12. Their base is what? Let's see, we have 8. This is 2. That's 6. So this is 3 inches, and that's 3 inches. So we have a base of 3 and a height of 8 cubed. Let's see, I have this already worked out. I got 896 inches to the 4th power for that bad boy. And you can do that as long as it is symmetric, meaning if I take the neutral axis here, it's all symmetric. Meaning if this were smaller, like this guy, you can't do that method, but regardless, because all these have to have the same neutral. I don't know why I'm even talking about this. That's old material, right? All right, let's talk about step number 3 then. I'm meandering today, I apologize. 3, let's go ahead and find out what our Q and our shear stress is as we move along this cross section. What do we, because we're asked to find maximum shear stress, but let's find it all the way out along the cross section. So let's take a look at, how do I do this? Let's do this, see if this is going to work for me. Paste. Oh, good, it did work. All right, let's take a look at this cross section again, and let's look at the neutral axis. We mentioned before it's where it's going to be maximum. It's what we care about probably most, right? So we said Q is equal to A prime Y bar prime. Well, my neutral axis is right at the midpoint. Let me move this. Oh, whatever. You get the idea. It's right here, right? Does that look like about the midpoint? Neutral axis. So what I'm going to do is I'm going to break it into 2 different shapes. So I'm going to have one shape here, and I'm going to have one shape here, and each one will have its own little y bar prime. That's kind of messy in there. But so instead of just saying a prime y bar prime, I'm going to say sum of a prime y bar prime. So what do I have here? Well, this, I'll call this shape number 1 and shape number 2. For shape number 1, I have an area of 2 times 4, so that's just base times height, right? Because this is 8, so to get up to here would be 4 inches. Times the distance down is that 2. And then I have plus that top piece, base is 8, height is 2. And then I have to go that 1 inch plus another 4, which is 5. And that gives me 96 cubic inches is my unit for that guy. Cool. So now I'm ready to actually find out the shear stress at the neutral axis. We said it's equal to VQ over IT. Maximum shear force was 800 pounds. 800 pounds. We have our Q at this location, 96 inches cubed. We have our moment of inertia, which I found to be what, 896 inches to the 4th. And then T, what is T? At this neutral axis, that means we want the shear stress right there. That is my T, which is 2 inches. 2 inches. Put that whole thing together, I end up with what? 42.86 P SI. Cool. And that is actually the maximum. I know that's what that problem asked for, but let's go ahead and look at some other interesting points because there's some cool stuff that goes on with this idea. All right, so let's look at y equal 1 inch. So at y equal 1 inch. And what that means is 1 inch up is what I'm saying. Actually, let's just paste this guy again and start all over, right? Make it a little easier on us. So what we're saying is we still have this neutral axis, which is at the midpoint right about there, neutral axis. I still have 2 shapes, but now what I'm saying is I'm going to move up 1 inch. So like maybe to here, right? So I have one shape here. The top one is actually the exact same. So when it comes to Q, what do I have? Well, for shape number 1, I have the same base of 2 inches, but now what is this business? Whoa, hey, knock it off. What is this business here? This is the hardest part. So the distance from it down. Well, remember this is 1 inch. So, and this whole thing was 4 inches. That means this is 3 inches and this is 1 inch, right? If I were to draw it like that. So what do I have? I have 1.5 right there. Let me draw it like this. We're going to say we have 1.5 plus that other 1 inch to get all the way down to the neutral axis. For the top flange, it stays the exact same because it's still same area, same distance down, meaning 8 times 2 times 5, giving me 95 inches cubed. So you see it hasn't changed a bunch. I haven't gone real far, but my tau at y equals 1. Then we have 800 pounds. We have 95 cubic inches. And then we have our 896 inches to the fourth. And we still have the same t value of 2 inches, giving me 42.41 psi. Rad. There are 2 of them. And remember, that's the same if I were to go 1 inch up or 1 inch down. So I could just say plus or minus 1 inch or something like that. All right, let's revisit this idea of T. Maybe you're already starting to think, hey, T, is it always 2? It is not. It's 2 until I get up until this flange, and then it would be 8 inches. But here's the interesting part. What's going on at y equal 4 inches, meaning right at that web flange interface? Let's take a look at that in particular. So we have something like this again. Let me add my neutral axis in here. Neutral axis. And now we're saying, well, what about right there? Ew, that looks horrible. Let's just put something like that. What about at that location? Well, let's look at our Q. Q is actually a little bit easier because my Q is just this guy, right? There is nothing because I want to know right at that location what my shear stress is. So Q is just 8 times 2 times 5, which is what, 80 inches cubed. And if I were to keep working up, by the way, it'd still work the same. So if I wanted to know, say at 1 inch, even above that, I'd have 8 times 1 times, I don't know, whatever that'd be, 4 plus 1 plus a half, 5 plus a half. Regardless, we have a Q value. All right, so what do we do about our shear stress? We have VQ over IT, so we have 800. We have 80, we have this 896. I'm dropping units to be quicker. What am I going to do about T? Well, I have 2 possibilities. It's either going to be 8 inches or it's going to be 2 inches. What's the answer? They both are correct. So we have 2 inches, and that is, what do I get here? 35.71 PSI, but I also could have said 800 times 80 over 876, 896, getting messy, gonna make a mistake because I'm going too quick maybe, but I could also have an 8 here, and if I had an 8 there, we got drop all the way down to 8.93 PSI. What we have is, because both exist, what this is called a discontinuity at the web flange, or anytime I'm going to have a change in thickness, I'm going to have this discontinuity interface. Meaning, if I were to repeat for the rest of the profile, paste, so for, I don't know, I did it in Excel, which I'll show in just a little bit, just to get even more exact. But let's say that, let me draw my neutral axis right here. Let's say I were to repeat it, what would be my overall shape? I'm going to draw a little reference line here that looks like this. All right, we know some values here, right? We know that it's maximum. So remember we said we have this parabolic shape, but we do have a maximum now, and that maximum was, I forget, 42.86. So we have 42.86. And then it decreases parabolically until I get to this web flange interface. So I'm gonna put a little dot here, so it'd be something like, and I know what 2 points are. I can tell you what those 2 points are. Those were my 42.41, 42.41, whatever. And then right here, what's happening is I have this point of discontinuity, and that means that at that point I have this 35.71, 35.71, but it's also, meaning I'm going to draw a line horizontally right here to like maybe there. It's also this 8.93 right here and here. And then if I were to continue the process, I'd find out it's still parabolically as I move along that flange as well, and I end up with a shape that looks like that. Now, like I said, I repeated this in Excel to show all the points, and you see something that looks like that. Looks a little interesting, but regardless, that is actually what we see with the maximum right there at the neutral axis, decreasing 0 at the top and bottom. So kind of a long video. Transverse shear stress seems like kind of a complicated subject, but hopefully you found that informative. Thanks for tuning in. Hopefully you learned something, and I'll talk to y'all next time. Thanks. See ya.